In the last video, we looked at a partial proof for the Maxi Min theorem for two-player or n-player zero-sum games. And in that partial proof, we discovered a method for finding mixed strategy Nash Equilibria for 2x2 zero-sum games. There's two-player zero-sum games where each player has two possible actions. The method we discovered there was rather cumbersome. It involved putting the game first into standard form and then solving some equations, simple equations, but solving some equations. And I promised at the end of that video that I would introduce a shortcut method. So here it goes. In this video, you will find the shortcut for solving 2x2 zero-sum games. These two-player zero-sum games. In fact, I'm going to run through an entire recipe for finding the Nash Equilibria of two-player zero-sum games, 2x2 two-person zero-sum games. So we start by using the Maxi Min strategy. The first step of the recipe, or the first step in our algorithm, is to use the Maxi Min strategy to determine if the game has any pure strategy Nash Equilibria. If it does, that's the solution. The value of those equilibria for player 1 is the value of the game. You're done. Move on to the next question. If, however, you discover that there are no pure Nash Equilibria, if, that is, you discover that the Maxi Min strategy comes up empty, then assume that the game has the following structure. That is, impose this rubric over the game. We'll call rows actions R1 and R2. We'll call calls actions C1 and C2. We'll call the intersection of R1, C1, A, of R1, C2, B, of R2, C1, C, and of R2, C2, D. We'll let the probability that row plays R1 be P, and that row plays R2 be 1 minus P, and the probability that call plays C1 be Q, and the probability that call plays C2 be 1 minus Q. Now, unlike in the proof where we were required to put the game into standard form, there are no restrictions on A, B, C, and D in this strategy. They can be positive or negative numbers. They can be greater than or less than any of the other numbers or any of the other outcomes. So there are no limitations here. There's no need to put the game into standard form to use this shortcut method. And our aim will be to find the values for P and Q for which PR1, 1 minus PR2, and QC1, 1 minus QC2, are in equilibria, or are in Nash equilibrium. Turns out that to do that, all we need is to set P equal to D minus C over A plus D minus B plus C, and set Q equal to D minus B over A plus D minus B plus C. And the value of the game, when we do that, will be A times P plus C times 1 minus P. Well, that seems easy. We just have to plug and chug those numbers. But why does it work? Why does it work out to such a simple formula for finding the mixed strategy Nash Equilibria of a 2x2 game? Well, think about it this way. When row plays her half of an equilibrium mixed strategy pair, she fixes the value of the game no matter what call does. She fixes the value of the game at her security level. And the same goes for call. If this is true, the expected utility of rho's equilibrium strategy against C1 must be the same as the expected utility of that strategy against C2, and the same holds for call. That is, the expected utility for rho is not dependent upon what call decides to do, because rho's equilibrium strategy sets the value of the game for rho, sets it at rho's security level. So no matter what call does, the value of the game will remain the same. That gives us a little bit of insight. The expected utility of rho against C1 is AP plus 1 minus PC, and against C2, it's BP plus 1 minus PD. That's just extrapolating from the game matrix that we see here on the previous slide. We've just multiplied through. And we know that they have to be equal. So we have AP plus 1 minus PC equals BP plus 1 minus P times D. And if we solve this equation for P, we end up with this equation up at the top of the slide. If we solve it, and we can do the same thing from call's perspective and solve this equation for Q. So just rearranging a bit here, we end up with P equals D minus C over A plus D minus B plus C. And that gives us a simple way of solving 2x2 games, 2x2 zero-sum games. So let's try it. What's the strategy, what's the Nash equilibrium of this game? Well, the first thing we should do is check whether there is a pure Nash equilibrium for this game. So we should use the Maxi Min strategy. The minimum for rho at A1 is -3, and at A2 it's 0. So the Maxi Min is A2 at 0. The min for call at A1 is -2, and at A2 is 1. -1, I'm sorry. So the Maxi Minimizer for call is also A2, but this time at -1, or A2, A1. So the Maxi Minimizers do not coincide. We don't have a pure strategy Nash equilibrium. So what's the mixed strategy Nash equilibrium of this game? Well, to figure that out, all we need to do is plug and chug. The probability with which rho is going to play A1 is just going to be D minus C, so that's 0 minus 2 over A plus D, which is -3 plus 0, minus B plus C, which is 1 plus 2, and that will give us 1/3. And we can do the same to solve for Q and find that it is 1/6, and discover that the value of the game is 1/3. The value of the game for rho is 1/3. Now, if we wanted to check our work, we could plug 1/3 in for P and 2/3 in for 1 minus P, or for the probability that rho plays A2. And we could then multiply that through and try a few different values for Q and 1 minus Q, and see that rho has in fact set the value of the game by playing this strategy. And we could do the same for call. And that would show us that we have in fact found a Nash equilibrium. We have in fact found a solution to the game where neither player has an incentive to unilaterally deviate given that the other player maintains that same strategy or that Equilibria strategy. All right, so there's your shortcut method. I advise you to use it whenever you have an opportunity because it's much simpler than applying the method we discovered in the last set of slides in the last lecture. That's all.